Okay, I, I think we're working. Testing, test. Okay. Yeah. All right. Okay. Happy Friday, and we have a long weekend, so that's nice. A little extra breathing room. Midterm season finally over. No, not you still week 9 midterms. Anybody? Okay, that's like the worst. The week 9 midterm. It's like, what's the point, right? Just okay. Let's look at what we'll look at. So we introduced k-means clustering, and then now we can do k-means clustering with kernel functions. So kernel functions, I don't know if you guys watched the SVM lecture, but there's kind of, you can apply a function, this quote kernel function, and kernel is one of those weird words that shows up in a whole bunch of different contexts with like totally different meanings every time, and so it can become like very confusing as far as like, oh, you have this kernel function, and then you have this kernel density, and you have this kernel this and kernel that, and it's like, what are you talking about? And they're all like different things. So, but anyway, we can apply a kernel function to our data, and then apply the k-means clustering algorithm in that sense here. Okay, so let's just review k-means clustering. We decide how many clusters, how many k clusters that we're going to look for, and then we use some kind of initialization method. Either we randomly assign points to the clusters, or we randomly select points to be the quote centroids of the clusters or whatever, and then you assign, once all the points have been assigned to a cluster, we calculate the centroids, and once you have the centroids, you associate values to the centroid that is closest to it. So just using Euclidean distance, you say, hey, which centroid is the closest, and then you iterate back and forth, reassigning the points, recalculating the centroids, reassigning points, recalculating centroids, so on and so forth, until no new changes are made, and then you say we've reached convergence. However, depending on your initial random assignments and points, if you say you're searching for 4 clusters, depending on your initial starting scenarios, you could end up with different final cluster assignments. Okay. All right. So again, here is just an simple example. I've got dots in red, black, and green, and then we will calculate the centroids. So here I've got red, black, and green, and then we assign the points that are closest to red and signs closest to black, points closest to green, and this is what we end up getting. Interestingly enough, only a couple points ended up close to green, like this point. So sometimes, again, by random chance, you could end up with like no points closest to green. That could happen, and then you just kind of have to re-roll. Otherwise, you're going to end up just with 2 clusters at the end. But here, when we say, hey, which point is closest to green, it's just like these 3 points right here. Okay. But then we say, okay, well, what's the centroid of everything in red? What's the centroid of everything in black? What's the centroid of everything in green? And we get that. And then we reassign the points. We say, all right, so now we say, like, okay, between red and green, like all of these points down here will get assigned to green. You can imagine like a line splitting, draw a line connecting red and green, and then something perpendicular to it. And then and that will kind of be your boundary. And so we get that, we reassign the points, then we recalculate the centroids, reassign points, recalculate centroids, and you keep going. And then I think at this point, no new assignments have been made. And so we will say that that is where it converged. And overall, that looks pretty correct as far as if I said, hey, identify 3 clusters, you would probably draw circles that look kind of like this. Okay, so we'll take a look at this idea of a kernelized thing, okay? And so a kernel function is basically you take in kind of two vectors, okay? So it could be, you could treat a point in 2 dimensions as a vector, or you could have a higher dimensional vector as well. And then when and you take these two vectors and then you put them in through the kernel function, you get like one value out, okay? So a simple example could just be like the dot product, okay? Is you take, you have a vector, you have another vector, you multiply component 1, and so on and so forth, right? That counts, okay? There is no, in that case, you don't have a transformation function. But a kernel function can also be basically the result, this inner product of two vectors after you apply some transformation function phi, okay? So we'll say if we have vector xa and vector xb, we can apply a transformation function phi, and I don't know, my LaTeX did something. These are supposed to be the same symbol, but this is like the cursive version, and this is the non-cursive version of phi. I don't know. Okay, so you have this function applied to xa, it transforms it. You apply the function to xb, and it transforms it. And then you take the inner product of that, and that's that. So the linear kernel, the transformation function is basically nothing. It's the identity function. So basically you just have inner product of xa and xb, and it's going to be the same thing as xa transpose xb, right? It's basically the dot product of the two vectors xa and xb. Here is an example of a transformation function. This one, your vector x exists in 2 dimensions, and when you apply this transformation function, it creates a 3-dimensional, the output of the transformation function is length 3, okay? So we go from 2D up to 3D, okay? And there is an equivalent kernel, right? So if I transform xa and xb, I'm going to transform xa into this 3-dimensional vector, xa1, xa2, and then xa1 squared and plus xa2 squared. And then I transform xb into this, xb1, xb2, xb1 squared plus xb2 squared. And then we'll take the dot product between these, or the inner product, whatever. And so we get xa1, xb1, first component times first component, second component times second component, which is xa2, xb2, and third component times third component, xa1 squared plus xa2 squared times xb1 squared plus xb2 squared. And if you look at that, this is equivalent. This part up here is the equivalent as just the original xa and xb, the inner product between them, xa dot xb, or I guess you could do xa transpose xb. And then over here, xa1 squared plus xa2 squared is the same as your norm of xa squared and your norm of xb squared. And so I'm just taking the product of the norm of xa squared and the norm of xb squared. Okay, so this is an example of a kernel function, and we get the results of this. And so you could go through the steps of taking your vector, transforming it, and then doing the inner product. Or if you just need the result, you can go straight to this thing, and they're equivalent. When back in the SVM lecture that I just kind of posted a video of it. Let me skip ahead. Okay, so here is
introducing the silencer cargo.
Okay. So this would be an example of doing SVM after applying a kernel thing. So the idea here is you have in SVM, the first example of SVM was you needed kind of linearly separable values, but here we have basically blue dots in the center and red dots surrounding it, and we don't have a linear boundary that can separate these things. But you could imagine applying this transformation function where we take each value in 2D and we project it into a higher 3D space. And so when you do that, if you take your 2D points and you project it into 3D, this is the resulting space. So the blue dots get projected up, and then the points that are farther away from the origin get projected even higher. And then in SVM, you can now draw a linear boundary. In 3 dimensions, that would be equivalent to a plane. And so now you have this boundary that separates the blue from the red. Okay, so that would be, that's the kind of the kernel trick applied to SVM. But we can do this a similar kind of thing where we project our data into a higher dimension and then we do k-means clustering. So here's another example of a transformation function, and this would be a kernel function. And so you can have this is a polynomial kernel where you have some kind of constant, some kind of power, gamma, okay? And, just for example, if you set gamma equal to 2 and you leave your constant 0, then what would happen is this is equivalent to using this transformation function. x1 and x2 become x1 squared, x2 squared, and then root x1, x2. And again, you can see if you plug in xa and xb, you get xa1 squared, xa2 squared, root xa1, xa2, xb1 squared, xb2 squared, root 2, xb1, xb2. And, taking the inner product, you'll get xa1, xb1 squared, and then xa2, xb2 quantity squared. And then the third thing, multiplied together, you get root 2 times root 2 is 2, and then xa1, xa2, xb1, xb2. And with a little bit of kind of just applying algebra, and you kind of factor this, you can see, oh, this is the equivalent to having xa1, xb1 plus xa2, xb2 quantity squared. Okay? And this is equivalent to xa transpose xb xa transpose xb quantity squared. Okay? And so, again, you have your kind of two-dimensional vectors. They get plugged into some transformation function. So far, our transformation functions go from 2D to 3D, but that's not a limitation. It can go from 2D to 2D, 2D to 5D, 2D to 100D. It doesn't matter. But then you take the inner product of those resulting transformed vectors, and when you take the inner product, you get back a single scalar value. Okay? So kernel function, you plug in vectors, you get back a scalar value. But it's equivalent to transforming them, then doing an inner product and getting your scalar value. Yeah, question?
So inner product basically means like element-wise multiplication.
Yeah, element-wise multiplication and then added up. Basically, you're kind of like your dot product. Yeah. Okay, there's other kernel functions. So we have the polynomial kernel, and then the Gaussian kernel, which you saw when you did your SVM homework. In your SVM homework, I had you play around with a gamma and a cost value and things like that. The weird thing about the Gaussian kernel, this radial basis function kernel, this link doesn't work. Oh, it does. Is that it is equivalent to an infinite dimensional this function that when we transform it, it transforms xa and xb into these infinitely long vectors. Okay, it's hard to imagine, right? But so these previous functions transformed it from length 2 to length 3. But technically the RBF, or the Gaussian kernel, transforms it from length 2 to length infinity. Okay? And then it takes the inner product and you get back a single scalar. It's based on the Taylor expansion of the exponential function. So that Taylor expansion technically goes on to infinity. I mean, you can truncate it and say like, okay, after 10 terms, this is like close enough or something. But at a theoretic level, when you plug it into here, it's like transforming it into a vector of infinite length. Okay. Okay, so we say all kernel functions are inner products of vectors after they've been transformed by this transformation function phi. But the thing is you don't even need to know what that transformation function is. I think it is helpful to know what the transformation function is to kind of learn and visualize how k-means clustering works with this kernel function being applied. But if you just want to cut straight to the answer, you don't actually need to know what that transformation function is. Okay? So the kernel function is an inner product for some arbitrary transformation. You can kind of substitute it in whenever you see kind of an inner product in the original space. Okay. All right. So in k-means clustering, what we do is we assign a point to a cluster based on its distance to a centroid. The squared distance of a point, okay, so if we have this centroid mu k, okay, we can do, what is the distance between some point n, xn, and the centroid of cluster k, and we can say, hey, the squared distance is x minus mu, xn minus mu k transpose xn minus mu k, all right? Okay, where's the location of mu k? Mu k is basically the mean of all of the x values that belong to that cluster. So you have the product between z and x, where z is 0 if it doesn't belong, it's 1 if it does belong. You take the product between z and x, add them up, divide by n being the sum of your z's, how many points belong to that cluster. And then this looks like a huge mess, and it is. But this is a way to express what is the distance to the centroid using just kind of the inner product. So we could say, all right, what is the centroid? I'm going to just replace the centroid of cluster K with the expression z, basically z times x times 1 over n. And then here I got basically z times x times 1 over n over here. And then we're going to take kind of the product of all of this, and you're going to get xn, x and transpose xn, first, inner, outer, last, okay? And you end up kind of getting this big, kind of this big mess. These two inner terms can be combined. So to kind of make sure because here you have a summation, I have two different subscripts here. I've got a subscript over m, and then I have a subscript over r, just an arbitrary letter choice, okay? And when you go over across all of the m values and across all of the r values, these two things are going to be equivalent, so they can be combined. But here you have kind of this double summation. You have to sum over r and sum over m. And so anyway, this is what you end up getting. And so you have kind of these inner products. This is a way for us to say, what is the distance between point n and the centroid of cluster K? Okay. And anytime we see this kind of inner product, xn transpose xn, we can say, well, what if we use a kernel function there? Okay, here I have xm transpose xn. What if I use a kernel function there? Here I have xm transpose xr. What if I use a kernel function here? And again, by using the kernel function, we don't actually need to transform our data from the lower dimension to the higher dimension. We can just kind of skip over that and get straight to the answer with the kernel function k. All right, let me give you your first view quiz answer, which is the letter E. E as an elephant. Okay, so now that we have a way to measure the distance between each point and the centroid of cluster K, we can revise our k-means clustering into this, okay? So we randomly assign points to each of the clusters, and then we calculate the distance between each point and each of the clusters. So we go to point 1 and we say, all right, find the distance to centroid of cluster 1, centroid of cluster 2, centroid of cluster 3. And then once we find those distances, we reassign the points. Okay. Here's kind of the weird thing. Now that we have a formula for the distance, and this distance formula doesn't actually require us to find the centroids themselves. Okay, so this back here made sense. You find your x, you find your centroid, you take the difference between x and the centroid, and you get that, and you square that distance. Okay, and you say, okay, well, this is my squared distance between each point and the centroid. But now I have a formula for getting the distance to the centroid that doesn't actually involve finding the centroid itself. It requires me to do this crazy double summation thing, but it doesn't require me to actually find the location of the centroid itself. Okay. So now my algorithm just says reassign points and then calculate distance to centroids. It used to be reassign points, recalculate centroids, calculate distance to centroids, reassign points. Okay. Now it's just reassign points, calculate distance to centroids, reassign points, calculate distance to centroids. Okay. And there's no recalculating of the centroids itself. Calculating the distance to the centroids does involve a little bit of, this slightly computationally expensive double summation thing, but you don't actually need to calculate the centroids themselves, which is going to be important for us because if we use, say, the Gaussian kernel, then the centroid exists in this infinite dimensional space. And so calculating what that centroid is not going to be possible because it's the coordinate is this infinitely long vector. Okay? But we don't need to know exactly where the centroid is. We just say, what is the distance to the centroid? And we're able to get the distance to the centroid, even if we don't know the exact location of the centroid. It feels very strange, but we have a formula for getting the distance to the centroid, even though we don't actually know what the centroid is. Okay, so you know what? Let's back up for a second, and let me just work through this very, very simple example. Okay, so what I'm going to do is I'm going to do kernelized k-means clustering 2 times. Okay, in the first run, I'm going to start off with 2-dimensional data, and then I'm going to actually do the transformation into 3 dimensions, because 3 dimensions we can calculate and we can visualize. And then we will do k-means clustering in 3 dimensions, and you'll see the resulting clusters. And then I will do it again, but this time I'll leave everything in 2D, and then we'll just use the formula that says, hey, what is the distance to the centroids using our kernel function, but we're not actually going to calculate the centroids. Okay, does that make sense? What I'm trying to do? We're gonna do it 2 times. One is we'll see the actual transformation and we'll say, all right, this is the new centroid in 3 dimensions, and here's the distance to the centroid. And then the second time, I'm going to just say, hey, we can just get those distances without actually finding the centroids, which is what I'm trying to say is possible, is that we can find these distances without actually finding the centroids. All right, so I'm going to have 8 points. I've got 4 points near the origin, 4 points far away from the origin. And this is so I've got 4 points here and 4 points far away. And if I just used plain old k-means clustering with Euclidean distance, well, I mean, if you had to cluster these, and I say, form 2 groups of similar points, what would you do? You'd probably put the 4 in the middle together in one cluster, and then you'd put the 4 on the outside in the other cluster, right? That kind of, there's something that makes sense about it. But if you used Euclidean distance as your measure of similarity, Euclidean distance will not put this dot and this dot in the same cluster, okay? They are at opposite corners, and according to Euclidean distance, these 2 dots cannot be more different from each other, okay? But there's something in us that says, they're different, but they belong together, right? and we don't want to split up these ones, okay? But according to Euclidean distance, this dot down here is more similar to this one than this one over here is to that one, right? Euclidean distance says this is really far apart, therefore they're really different. But something in us says, yeah, I think we should do this. So what we're going to do is we're going to transform them into 3Ds. We're going to go from x1, x2 to x1, x2, and then x1 squared plus x2 squared. Okay, and I can do this in a 3-dimensional thing. Let me run. Okay, so I'm going to run this, run that. Okay, so there's my plot there. Okay, that's the, okay, so here we go, I think. Did that work? Sorry. Let me run this. Okay, we'll find the means with dplyr, and then I'm going to plot this here. Okay, so here we go. Oh, it's a little hard to see. So I've got, when we randomly assigned them, we had 1, 2, 3, 4, 5 assigned to red, and then 1, 2, 3 points assigned to blue. And then we said, okay, what is the mean of the cluster A, which is blue, and what is the mean of cluster B, which is in red? Okay, and these are the centroids. It's plotted in 3D. It's hard to see, so it will be easier. So I think this is like what you are seeing is this view is this view right here, okay? But I think it's easier to see if so here you can see I've got 1, 2, I don't know if you can see the colors okay, but you got 1, 2, 3 points in red and 2 points in red down here, so the center of the red centroid is closer to the, I guess, ceiling of the box, and then you got 2 blue down here and 1 blue up here, and so therefore the centroid of the blue dots are closer to the bottom, right? So here it is like this, and then if you take a top-down approach, you can see I got 1 over here and 2 over here, and so the centroid of the blue is kind of in between there, and you got 1, 2, 3, 4 red and 1 red over here, and so therefore the centroid of red is like that. So this is kind of what it looks like in 3D. So these two dots right here represent the centroids of the red and the blue. And then now that we have these centroids of the red and the blue, we're going to say, all right, calculate the distance between each of the points to the centroids, and then reassign the points to the nearest centroid. Okay, so if I do that, what will get assigned to the red centroid and what will get assigned to the blue centroid? The points on the floor will get assigned to the blue centroid, and the points on the ceiling will all get assigned to the red centroid, right? So, so that's what's going to happen. So here I can calculate, okay, what are the coordinates of the blue centroid? The coordinates of the blue centroid are, so top down, negative 0.667, positive 0.667, and then your z coordinate would be 2.68. And then what is the centroid of the red? Okay, over here is I'm sorry. These are not the okay, so this is the coordinate and then the distance. Okay, and then we calculated, all right, what is the distance between the centroids and these different dots here? And so these are the different centroids, I mean the different distances. So we said, what is the distance from each of these 4 points to the blue centroid? And it's like 7.98, 8.25, 7.7, and 7.98. Okay, and then what are the distances to between these 4 points and the red centroid? And they're all around 23.26, 23.1.1, 23.42, 23.26, right? So they all have very kind of similar values, which makes sense because they're all kind of very close to each other. And then these points down here, we asked, okay, what is the distance from here to the blue centroid? All right, and they're like 37.1, 42, 37.1, 31.85 distances to the blue. And then we say, okay, what is the distance to the red centroid? And those distances are like 18.5, 15.3, 18.5, and 21.7. So we can see, yeah, this corner and this corner will have the same distance to the red centroid because they're like mirrors of each other. And then this one is closer. This distance of 42 is, this corner has a distance of 15 to this and 42 to the blue. And then this corner has a distance of 31 to the blue and 21.7 to the red, if you look at it from this way. Okay, so when you reassign them, yeah, the 4 points on the bottom based on these distances get assigned to cluster 1, and then the 4 points on the ceiling get assigned to cluster 2. And then so if you run this second thing, then calculate these distances. So now these are the cluster assignments at the end. All 4 in the ceiling are assigned to red, and the centroid of the red cluster is up there. All 4 on the floor are assigned to the blue cluster, and the centroid of the blue cluster is down here. So not super interesting, but there you go. We have clustered our points into blue and red, and the ones in the center got assigned to blue, and the ones on the edges got assigned to red. So that's that, and then you can recalculate the distances, and then you're going to see, yeah, there's no reassignments here. Everything is assigned to their nearest centroid. Okay, so that is what it looks like if you transform from 2D into 3D, and then you calculate your distances and you reassign the things. Okay, and I'm going to try to show you that we could leave everything in 2D, and we can, by using this kernel function, we can get the distances to the centroids without actually calculating the location of the centroid. Okay, so the things to keep, the values I want you to remember are the values on this page 36. Okay, page 36 is I transformed them into 3D and then I calculated the distances to centroid A and centroid B. Okay, and basically we want to say, can we get these same numbers even if I don't actually calculate the coordinate of centroid A and centroid B? So here I start off with the same random assignments, and then I have to implement this kind of ugly formula here, okay? But if I implement this ugly formula, so one involves this kind of this calculation of this giant K matrix between M and R. If we go over kind of the double summation of this, I'm working through each of these terms here, this double summation here, the summation over that. These are the distances to centroid A, okay? Even though I never actually calculated the coordinate of centroid A. This feels like there was a lot of work here because we have to do this double summation and calculating of this matrix. But if you do this, you can get the distances to centroid A, all right, despite never actually calculating the location of centroid A. So look at slide, I guess, 36. Look at these numbers: 7.98, 8.25, 7.7, 7.98, 37.19, 42.525. And you get those same values, right? 7.98, 8.25, 7.7, 7.98, 37.19, 42.525. So we're getting those distances, the distances to centroid A, despite not finding the actual location of centroid A. Okay, same thing, these are the distances to centroid B. And again, comparing it back on slide 36, sorry, I put slide 35 in the notes, but slide 36, we have these distances 23.2, etc., 18.5, 15.3. We have those same distances, 23.2, 18.5, 15.3. Same distances. And so we're able to calculate the distances to the centroids without calculating the actual location of the centroids. And then we can say, all right, which one has the smaller centroid distance to each centroid? And then we can redo our assignments there. Okay, let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. Okay, and then so again, redoing it, doing kind of the distances to all of the centroids involving the double summations and all of that. I can recalculate the distances to the centroids without actually calculating the coordinate of the centroid, which will be important because if we do, say, the Gaussian kernel, the coordinate of the centroid, again, exists in an infinite dimensional space, and we're not going to be able to calculate that. That's just our computers can't do that. Okay, so here's just another example. Again, this is artificially created data, but I've got kind of a ring of points on the outside, a ring of points on the inside, and we want to kind of cluster these into two things. If we just did k-means clustering, again, it will never put dots over here and dots down here in the same cluster because according to Euclidean distance, they are very different from each other. Okay, but here we will just kind of do some random assignments and stuff. I'm going to apply the Gaussian kernel, and we will recalculate the distances to these mystery location centroids, and this is start off my random assignments, and then I kind of just calculate the distances and reassign points. And after one iteration, this is what it ends up. I have no idea what it looks like in this projected space. Again, the projected spaces exist in infinite dimensions. So somehow these points are closer to each other in this infinite dimensional space than the other ones, and then we recalculate kind of our distances to the centroids. And eventually we end up getting this, and it has correctly clustered points on the outside and points on the inside into two different clusters here. I have this is a silly example because part of this feels very mysterious, like almost magic, right? In that, how can we calculate the distance to the centroid if we don't actually know where the centroid is, right? There's this inherent thing of like, we shouldn't be able to do this, right? Because I'm saying we're going to calculate the distance to centroid A, and you go, oh, great, where's centroid A? And you go, oh, don't worry about it. We don't actually need to know where centroid A is. And so the location of centroid A is left undefined. And instead, the way, if you look at the math, what it's doing is it's kind of doing a product between your point and every other point that currently exists. Okay? And so, forgive this silly example, okay? So I put up these actors, okay? Because, I don't know, I enjoy superhero movies and stuff. And you might like try to cluster certain actors together, right? And so here you have, Chris Evans, Chris Hemsworth, Jason Momoa. These play kind of the like superhero, muscular, brawn, very powerful kind of characters, okay? And then I don't know if you're familiar with these actors, okay? I mean, and they play different roles, right? The kinds of roles they play are maybe their power is more in their wit and their as when faced with a problem, they would probably think about it before starting to throw any kind of punches or something like that, right? And so we might try to, I might cluster them together, based on their roles here. And so let's say you get a new actor, okay? And I say, try to put him into a cluster. Well, what is the centroid? Is there a centroid for these actors? And that doesn't quite exist, right? The centroid for the actor would be like, what is the average of these different people? And we, what does that even look like, right? But we might have some measure of like, okay, how similar or how dissimilar are two people or characters or their roles. And we might be able to measure kind of a quote distance by saying like, okay, we'll measure the distance between, whoever our new actor is, how different or similar are they to, these currently, the ones that have already been clustered, okay? How different or how dissimilar are they? And so you kind of measure the distance between the person, your new case or whatever, to every other point without actually calculating what the centroid is, right? Because the centroid, as far as something like people, that would be like it's just kind of this weird concept that doesn't quite exist. You might have some kind of measure of similarity, and I don't know how you would do that in the first place. But if you have a way to kind of measure distance, or a way to measure, some kind of metric there, you might be able to find the distance between that point and every other point, and then calculate the distance to the quote centroid accordingly, despite not actually having calculated the centroid itself. Okay, let me give you your last view quiz answer, which is the letter B. B as in bear. B. Okay, we'll end things here, and have a good weekend. We'll see you Wednesday.